Okay, let's dive into a problem that really hits you squarely when you're building serious AI and machine learning models.
Hmm.
You've got these incredibly complex systems, maybe thousands of parameters, and you absolutely need to understand the uncertainty.
Yeah, that's key.
Like, what's the probable range for this parameter? Or what's the likelihood of a certain outcome happening given all the randomness involved?
Right.
And trying to figure that out by calculating every single possibility,
Yeah.
it's like counting sand grains on every beach. You
No,
can't.
exactly. You just can't. The numbers get way too big. The dependencies between things are too intricate,
Mhm.
especially when you're dealing with, high dimensional spaces.
High dimensions meaning lots of variables interacting.
Yeah, or even if it's not that many variables, maybe the shape of the probability distribution you care about is just
Yeah.
weird. Not a nice, simple bell curve.
Okay.
In those cases, direct calculation or even simple approximations, they just, uh, they fall apart. The cost computationally is just way too high.
So we hit a wall with the standard math toolbox, but that doesn't mean we just give up on understanding uncertainty,
No,
right?
not at all. It means we need to get clever
Get clever how?
through simulation
Yeah.
by using randomness, but in a very structured, very smart way to sort of explore that impossible space and pull out the insights we need.
Ah, okay. So using randomness to understand randomness.
Precisely.
Yeah.
And that's what we're going to unpack today in this deep dive. We'll look at some really powerful simulation methods.
Like what?
Well, we'll start with the foundational idea, Markov chains, then move to the general technique of Monte Carlo simulation.
Okay.
And then we'll see how they combine into what's really the workhorse for sampling these complex distributions, Markov Chain Monte Carlo, or MCMC.
MCMC, heard of that.
And we'll cap it off with a more cutting-edge technique, Hamiltonian Monte Carlo, HMC.
Right, HMC. Sounds intimidating.
It can seem that way, but the goal here is really to demystify these ideas. We want to show why they're such essential tools in AI and ML today.
So not just the math, but the why and the how.
Exactly. Giving you the understanding to not just, click a button in some software, but to grasp how it works. And crucially, how to know if you can trust the results. Practical knowledge.
Without getting totally lost in the weeds.
That's the plan. We'll see how these simple-sounding probabilistic rules, combined with computing power, let us approximate answers and understand uncertainty in ways that were just impossible before.
Okay, sounds good. So let's properly set the stage then. Why do we need simulation? You mentioned uncertainty in AML is everywhere.
It really is. Think about it. You train a model, you get parameter values. But are those the exact right values? Probably not.
Right, there's always some error, some noise in the data.
Exactly. So you don't just want one single best guess for each parameter. You want to know the likely range. What's the whole probability distribution of those parameters, given the data you saw?
Like in Bayesian modeling.
Bayesian modeling is a perfect example. You start with some prior belief, you get data, and you update it to a posterior distribution. That posterior is the answer you want. It captures all plausible parameter values,
But calculating it directly is the hard part.
especially for realistic models. Many parameters mean this distribution lives in a super high-dimensional space, calculating its exact shape. Intractable.
And you can't just lay a grid over 1,000-dimensional space and checkpoints.
No way. The number of points would be astronomical. Forget it.
Even if it's not that high dimensional, the shape is weird, like multiple peaks or strange correlations.
Right. Then simpler approximations, like just assuming it looks like a multi-dimensional bell curve, a Gaussian, that often just won't cut it. You'd miss the real structure,
Okay, so direct calculation is out. Simple approximations might be wrong.
which leads us to simulation. Instead of calculating the exact answer, we generate lots and lots of samples from the distribution we care about.
Samples, like drawing examples.
Exactly. If we draw enough samples, and importantly, if they're representative of the distribution, then the collection of samples itself starts to look like the distribution.
Ah, so the samples show you the shape.
They do. And from that collection of samples, you can estimate all sorts of things: the average value, the spread, credible intervals, probabilities of interest.
It's like that analogy of understanding average income, right? You can't ask everyone in the country.
Perfect analogy.
So you take a random sample of people, ask them, and use that sample average to estimate the whole country's average. The key is getting a good random sample.
A representative sample.
Wow.
And the more samples you take, generally, the better your estimate gets. That's a core principle here.
Okay, the overall strategy makes sense. Let's dig into the first piece you mentioned, Markov chains. What's the absolute core idea there?
The absolute core is the Markovian assumption. It's often called the memoryless property.
Memoryless.
Yeah, it basically says, if you know the current state of a process, the future only depends on that current state.
Hmm.
How you got to that state, the history, it doesn't matter for predicting what happens next.
Huh. So only the present matters for the future probabilities?
Exactly. It's a stochastic process.
Yeah.
Meaning it involves randomness, but it follows that specific rule about memory.
Like the classic weather example. Whether it rains tomorrow only depends on if it's sunny or cloudy today, not if it was sunny all last week.
That's a simple illustration, yeah.
Mm-hmm.
Or think about the drunkard's walk example. Someone stumbles between, say, home, the pub, maybe somewhere else.
Okay.
If they reach home, maybe they just stay there. That's an absorbing state. Their next location, staying home, depends only on their current location, home, not the zigzag path they took.
Got it. So a Markov chain is defined by its possible states.
Right, the different possibilities like sunny, rainy, or home, pub.
The state space, which is just the set of all those possible states.
Correct.
And the transition operator or transition probabilities. That tells you the chance of moving from any state to any other state.
Precisely. You can draw it as a diagram. States are nodes, arrows show possible transitions, and the arrows have probabilities written on them.
Okay. How does this connect to AI or ML? Seems a bit abstract.
Well, a really practical connection, especially in older or simpler natural language processing, is word prediction, like n-grams.
N-grams, right. Like predicting the next word based on the previous one or two words.
Exactly. When your phone suggests the next word, the probability it assigns often depends primarily on the last word you typed, or maybe the last two. That's using a Markov-like assumption. The immediate history matters most.
So it's memoryless in the sense that it doesn't consider the whole paragraph you wrote before.
Pretty much, yeah. Real language models are more complex now,
Right.
but the anagram idea is rooted in that Markovian concept.
And you also mentioned hidden Markov models, HMMs.
Right, HMMs are an important extension. There, the underlying Markov process itself is hidden. You don't observe its states directly.
Okay.
But those hidden states influence something you can observe, like speech recognition. The hidden states could be the sequence of phonemes, the basic sounds someone intends to say.
Ah, you don't see the phones directly.
No, but you hear the audio signal, which is the observable process influenced by those hidden phones. HMMs were huge for figuring out that mapping.
Okay, interesting. So Markov chains give us these memoryless sequences. How do we then leverage randomness for estimation? That's Monte Carlo.
Yes, Monte Carlo simulation is a much broader idea. It's basically any technique that uses repeated random sampling to get numerical results, named after the casino because chance is fundamental.
Like rolling dice over and over.
Exactly. The basic recipe is identify your uncertain inputs, figure out their probability distributions, then repeatedly draw random values from those distributions.
And then?
You run your model, or whatever process you're studying, using those randomly drawn inputs.
Yeah.
You do this thousands, maybe millions of times, and collect all the outcomes.
And the magic happens when you look at all those collected outcomes.
Yes. If you want the average outcome, you average your simulation results. If you want the probability of something happening, you count how often it occurred in your simulations and divide by the total number of runs.
Mm-hmm. The coin flip example is perfect here. Flip it 10 times, you might get 7 heads. Weird.
Right.
Flip it 10,000 times, you're going to get really, really close to 50% heads.
That's the law of large numbers. The average result over many trials converges to the true expected value. The roulette example also shows this, and regression to the mean wild swings early on tend to average out.
So Monte Carlo is super versatile. It lets you tackle problems where direct math is just too hard.
Absolutely. Estimating complex probabilities, finding areas or volumes like estimating pi, by randomly throwing darts at a square board with a circle inside.
Right, see how many land inside the circle versus the square.
Or understanding the distribution of possible outcomes in a complex system with lots of uncertain parts. All Monte Carlo territory.
And practically you need good random number generators, right? Like
Yeah.
from libraries.
Definitely. Libraries like NumPy in Python, or the built-in random module, are crucial for generating those random inputs according to the distributions you need. Then you run the simulations, collect results, do stats.
But the key takeaway is that you get an approximation.
Yes, always an approximation, but often a very, very good one, especially if you run enough simulations.
Okay, so Monte Carlo uses random samples for estimation. Markov chains model sequences. Now let's put them together. Markov Chain Monte Carlo, MCMC. This is for that specific problem we started with, sampling from complex probability distributions.
Exactly right, because basic Monte Carlo helps estimate an outcome of a process with random inputs. But MCMC is different. It's designed to generate a sequence of samples that themselves look like they were drawn directly from your target probability distribution.
Even if that distribution is high-dimensional and weirdly shaped and you can't write down its formula easily.
Precisely. That's the goal. We need to understand the whole shape of the distribution across all parameters, not just one number. Grid search is out. Simple approximations are risky.
So MCMC builds a Markov chain to do this.
Yes, it constructs a very special Markov chain. The states in this chain are the actual parameter values you're interested in points in your parameter space. And the chain is designed so that, in the long run, the amount of time it spends visiting any particular region of that parameter space is directly proportional to the actual probability density of your target distribution in that region.
So it hangs out longer in high probability areas.
Exactly. And the sequence of states it visits, those are your samples. They form a collection that represents the target distribution.
That King Markov parable helps here, right? Visiting islands based on population size.
Yeah, it's a great intuition pump.
Yeah.
Islands are parameter values, population is probability density. King Markov wants to visit islands proportionally to their population.
How does he do it? The Metropolis algorithm.
Metropolis is the simplest MCMC. From his current island, current parameter value, he randomly picks a nearby island to potentially move to. Proposes a new parameter value.
Okay.
Now, the decision rule, if the proposed island is more populated, higher probability density, he always moves there. Always accept.
Makes sense. Go uphill.
But if the proposed island is less populated, lower probability, he doesn't automatically reject it. He accepts the move sometimes with a probability equal to the ratio. Population to proposed island. Population of current island.
Ah, so he sometimes goes downhill too.
Yes. That's absolutely crucial. It lets the chain escape from local probability peaks and explore the entire landscape. That specific acceptance rule mathematically guarantees that over time, the visits are proportional to the population. Probability density.
That acceptance ratio.
You turn.
Key proposal. That's the core.
That's the core of Metropolis. Seems simple, but it works. However.
There's always a however.
Yes. Basic Metropolis has a big practical problem, especially in high dimensions. The step size.
Yeah.
How far away should the proposed island be?
Right. If you propose tiny little steps.
Then you almost always accept, because the probability doesn't change much. But you explore so slowly. Each sample is almost identical to the last one. Highly correlated samples takes forever to see the whole picture.
And if you propose big jumps,
then you're likely to land somewhere with near zero probability compared to where you are, especially in high dimensions where most of the volume is out in the low probability tails.
So that ratio P proposal, P becomes tiny.
Right. And your acceptance probability is tiny. You reject almost every proposed move. The chain gets stuck, barely moving.
So you're stuck between exploring too slowly or not exploring at all.
That's the trade-off. And it gets really bad in high dimensions or for complex correlated distributions, makes basic Metropolis very inefficient.
Okay, that sets the stage perfectly for needing something better. Hamiltonian Monte Carlo, HMC.
Exactly. HMC is a more advanced MCMC method specifically designed to tackle that step size problem and explore high-dimensional spaces much more efficiently. It uses this really elegant physics analogy.
Physics? Oh.
But don't worry, it's intuitive. Think of the negative logarithm of your target probability distribution as defining an energy landscape, like a hilly terrain or a ski park. High probability means low potential energy.
Okay, so the bottom of the valleys are the high probability spots.
Precisely. Now, imagine your parameter values, Q, or the position of a particle in this landscape. HMC then introduces a fictitious momentum, P, for this particle.
Momentum, like how fast it's moving.
Kind of. Together, position and momentum define the Hamiltonian, which is the total energy. Potential energy, from position probability, plus kinetic energy from momentum.
Okay, so we have a particle with energy in a landscape. Now what?
Instead of random jumps like Metropolis, HMC simulates the physical trajectory of this particle. You give it a random kick, a random momentum, and then you let it roll or slide through the landscape according to Hamiltonian dynamics.
And the landscape guides it.
Yes. The gradient of the potential energy, which is related to the gradient of your log probability, acts like a force, pushing the particle downhill towards higher probability regions.
Ah, so it uses the slope information.
Critically, yes. And these simulated trajectories are designed to conserve energy, or technically preserve phase density. They're symplectic. This means the particle can naturally follow the contours and curves of the high probability regions.
So it can make these long, efficient moves across the space, guided by the shape of the distribution.
Exactly. That's why it's so much better, especially when parameters are correlated. It doesn't just randomly stumble. It follows the grooves in the landscape.
How does it actually simulate that trajectory? You can't solve the physics equations exactly right.
Right, not for complex distributions.
Yeah.
So HMC uses numerical integration. It takes small steps in time to approximate the trajectory. A common method is the leapfrog integrator.
Leapfrog. Why that one?
It's particularly good at preserving those energy-like properties over many steps. Much better than simpler methods like basic Euler integration. Keeps the simulation stable and accurate.
Okay, so let's walk through one HMC step to get a new sample.
Sure. First, you give your particle a random momentum p. Just draw it randomly, usually from a standard Gauss check.
Step 1, random kick.
Step 2. Use the leapfrog integrator to simulate the particle's path for a certain number of steps, let's say L steps, using a small step size epsilon. This simulation takes you from your current position q and momentum p to a proposed new position q and momentum p at the end of the trajectory.
Step 2. Simulate the physics for a bit.
Step 3. Apply a metropolis-style acceptance step. You calculate the change in the total energy, the Hamiltonian, between the start and end of the trajectory. Because of the numerical errors in leapfrog, energy isn't perfectly conserved.
So it's not guaranteed to be a perfect move.
Correct. So you accept the proposed state, QP, with a probability related to this energy change, typically μ 1 x spade delta h. If the energy increased, which shouldn't happen much with leapfrog, the acceptance probability drops.
But because leapfrog is good, that acceptance probability is usually very high, much higher than basic metropolis.
Generally, yes. Much higher. You waste far fewer proposals. That's the efficiency gain you get to explore further with each accepted step.
And the key ingredient for simulating the trajectory was the gradient, the slope of the log probability. Where does that come from?
That's where automatic differentiation, or autodiff, comes in. It's a computational technique.
Autodiff, like in neural networks.
Exactly the same underlying technology. Libraries like STAN, which is famous for HMC, or TensorFlow probability, PyTorch, they use autodiff to automatically calculate the exact gradients of your log probability function directly from the model code you write.
So you define your model, and the library figures out the gradients needed for HMC automatically.
Yes, you don't have to do calculus by hand, which would be impossible for complex models. Autodiff handles the heavy lifting of getting those crucial gradients accurately.
Okay, so the complexity is kind of hidden by the software. But understanding the physics analogy helps understand why it works so well.
Precisely. It guides the exploration intelligently.
Which brings us to actually using this in practice. If I'm an engineer using, say, STAN or PyMC, what do I need to know?
Well, you need to know about the tuning parameters HMC uses. The main ones are that leapfrog step size, epsilon, and the number of leapfrog steps per trajectory, L.
Epsilon and L, what do they do?
They control how the trajectory simulation works. Finding good values is crucial for efficiency and accuracy. Too large an epsilon, the integration becomes inaccurate, leading to rejected proposals. Too small, and you take tiny steps, which is slow. Too few L steps, you don't explore far. Too many, you might loop back on yourself a U-turn, which is inefficient.
So tuning these is important. Do I do that manually?
Often, the software libraries have sophisticated automatic tuning procedures, especially during a warm-up or burn-in phase before they start collecting the samples you'll actually keep. But understanding what they control is helpful.
Okay, so the sampler runs, potentially tunes itself. Then it gives me a ton of samples. How do I know if they're any good? Diagnostics.
Diagnostics are absolutely critical, non-negotiable. You must check them.
Like what? First thing?
Trace plots. Just plot the sampled value for each parameter against the iteration number.
Yeah.
You want to see something that looks like a fuzzy caterpillar.
Fuzzy caterpillar.
Yeah, meaning it's rapidly exploring a stable range of values, mixing well, not getting stuck in one place, flat lines, or trending wildly upwards or downwards. It should look like stationary noise.
Okay, visualize the samples. What else?
Run multiple chains, always. Start the sampler from different dispersed random initial points in the parameter space, maybe 3 or 4 chains.
Why multiple?
To check for convergence. All the chains should end up exploring the same distribution. If one chain finds a different probability peak than another, your sampler hasn't run long enough or isn't working properly.
And there's a number for that?
Yes. The R-hat statistic, often written, it compares the variance within each chain to the variance between the chains.
Yeah.
You want R-hat to be very close to 1, ideally less than 1.01 for all your parameters. If it's high, like 1.1 or more, the chains haven't converged. Big red flag.
R-hat less than 1.01. Got it. Next.
Effective sample size, ESS, sometimes called NEF. Because MCMC samples are often correlated, the next sample is usually close to the current one, a chain of, say, 1,000 samples isn't necessarily worth 1,000 independent draws.
Ah, so ESS tells you how many independent equivalent samples you have.
Exactly. It accounts for the autocorrelation. You want a high ESS relative to the total number of samples you drew post-warm-up. Low ESS means your sampler was inefficient, mixing poorly, and you might need to run it much longer or rethink your model.
Makes sense. More effective samples means more reliable estimates. Anything specific to HMC?
Yes, a very important one. Divergent transitions. These are specific warnings HMC gives you during sampling. They happen when the numerical integrator goes seriously off the rails, often in areas of high curvature or complex geometry in your probability landscape.
Is that bad?
Very bad. A high number of divergent transitions means the sampler is struggling to explore certain regions correctly. It might be missing entire parts of the probability distribution, which could seriously bias your results. You want zero, or at most a tiny handful, of divergences after warm-up.
Okay, so check trace plots, run multiple chains, check R-hat, check ESS, and specifically for HMC, check for divergent transitions.
Yes. If any of these look bad, you can't trust your results.
Yeah.
You need to investigate, maybe run the sampler longer, reparameterize your model, or adjust tuning parameters if possible.
Phew. Okay, that's a lot, but it seems crucial for trusting the output. So bringing it all together, why does all this matter so much for someone working in AI or ML today?
Because these methods, especially MCMC and HMC, are what allow us to move beyond simple models and point estimates. They let us build complex, realistic, probabilistic models and actually fit them to data.
And crucially, quantify the uncertainty.
Yes, that's the huge win. You don't just get one answer, you get a whole distribution of plausible answers. You can understand the uncertainty in your parameters, make predictions that come with uncertainty intervals, and see how errors might propagate.
So things like Bayesian neural networks, understanding the uncertainty in the weights.
That's one application. Or building sophisticated models for complex data structures. The source mentioned an item response theory model for wine tasting scores.
Right, modeling the judge's biases to get a better estimate of the underlying wine quality.
Exactly. You need MCMC to properly estimate all those judge biases and the wine quality simultaneously, accounting for all the uncertainty. These methods give you the power and flexibility to build models that truly reflect the complexity and randomness of the real world.
It's a richer, more honest picture than just finding the single best fit line or value.
Absolutely. It unlocks a deeper level of understanding.
Okay, so we've covered a lot of ground. From the basic memoryless idea of Markov chains to using raw randomness for estimation with Monte Carlo,
Yep.
then combining them into MCMC, the workhorse for sampling complex distributions.
Right.
Culminating in HMC, the sophisticated, physics-inspired approach that uses gradients to explore efficiently.
It really is a fascinating progression, building these ideas on top of each other. A synergy of probability theory, physics intuition, and computational power.
And thankfully, a lot of it is packaged up in powerful software libraries now.
Making these advanced techniques accessible to practitioners, which is fantastic.
So for everyone listening, here's something to think about. Consider the next complex system or model you work with or analyze in AI and ML.
Yeah.
How much are you currently simplifying things when it comes to uncertainty? Are you relying mostly on single best guess values, point estimates, ignoring the what-ifs and the ranges?
Good question.
How could these simulation techniques, MCMC, HMC, give you a more complete, more honest, and maybe even more useful picture of the possibilities? What new questions could you start asking if you could actually draw samples directly from that complex high-dimensional distribution underlying your problem?